Okay, we want to look at some notes on how to find or solve for Newton's second law. And remember in the notes that we looked at Newton's second law and weight, that weight is just a function of the force that gravity applies to a mass. And so the G in the second equation here, the G stands for gravity. So the force of gravity equals mass times the acceleration due to gravity, which is 9.8. And this is going to be weight. Okay. Weight is the force of gravity. So that's F with a little g. All right, and then force equals mass times acceleration. What we'd usually say is net force. Net force. And the way you'll usually see that is we'll say F with a small net at the bottom. All right, so that's kind of our background if you've been missing some classes. So let's see what's going on. Don't worry about that. All right, Newton's second law says that F equals ma. The acceleration of an object is proportional to the force acting on it and inversely proportional to its mass. When Newton wrote his paper, he talked about the acceleration of the object is equal to the force divided by the mass. So when they use terms like it's proportional, that means it's on top. If force gets big, okay, let's say we have a big force divided by a mass. That means we're going to have a big A. If we have a little force divided by mass, so if I can make these, I'm not as good at this as, okay, small force over mass, we're going to have a little a. And that makes sense. The bigger the force, the more acceleration we're going to have. And it's inversely proportional to the mass. That means that if we have a force and it's divided by a small mass, we're going to have a large a. If we have a force applied to a large mass, we're going to have a smaller a. And that's the concept behind this. Mathematically, you take, we've rearranged it so it says F equals mass times acceleration. Force equals mass times acceleration. We have our units over here in the little box. Force is measured in newtons. Mass must be in kilograms. So if they give it to you in grams, you have to rearrange, you have to solve for the number of kilograms first. And your acceleration is in meters per second squared. The other equation is really the exact same equation, but what they're saying is gravity always pulls an object down with a gravity that is acceleration is equal to negative 9.8 meters per second squared. Now, whenever that object isn't being in free fall and that object is being weighed, we put it on a scale. What we're actually doing is we're saying that gravity pulling down is going to be equaled by a force that pushes up that is equal to the force of gravity pulling it down, and we call this weight that's pushing up, and we call this going down the force of gravity. And we say the force of gravity and weight are equal to each other. So when we do that, when we talk about what's the weight of the object, we use a positive 9.8. So let's look at the math. Here it gives us a 75 Newton force pushing against a person who has a mass of 60 kilograms. So we're asked to find the acceleration. The formulas are up at the top. You might not on your worksheet have this last one, so go ahead and add it. We're asked to find the acceleration, so we're going to set it up as A equals F over M. That's going to be F, which is 75 Newton force. There's no guessing here. That's going to tell you it's a force of 75, and we're dividing by the mass, which is 60. So put that in your calculator, and you'll get 1 point something. I'm not going to solve every problem here, just showing you how to work one or two problems. And the idea is this is a reading exercise as much as anything else, because you have to know that kilograms measures mass. You have to know that meters per second measures speed or velocity. You have to know that seconds measures time. And you have to know that meters per second squared measures acceleration, although usually we will tell you that it is accelerating at something, so it's more reading. But you have to know the mass, and you have to know the velocity and time for sure. Everything else, we will tell you what's going on. We won't just say 75 newtons. We'll say, hey, a force of 75 newtons. So it's reading. All right, then you have some other problems. Hold on just a sec. right, sorry about that. I had to set up what I was going to show you to work. Okay, so the figure shows a block being pulled along the floor. Find the net force. Net force is when you add up all the forces. So we're adding up this force that's to the right and the force that's to the left. And what you'd say is F net equals 50 being pulled to the right plus 10 being pulled to the left. So if they're going opposite directions, you're going to subtract. So we're going to subtract these two numbers. We're still going to call this adding forces because we could have a lot of forces acting up on this. And we've done this with vectors. The reason we practiced vectors was to get you ready for Newton's laws. So 50 to the right minus 10 to the left gives us 40 newtons to the right as our net force. Now they want to know the acceleration on the object. The acceleration is equal to the net force divided by the mass. It's always the net force that's going to cause the acceleration, because we didn't even talk about the fact that gravity is going to be pulling this sucker down and that the floor is going to be pushing it up with a force that is equal to the force of gravity. So we haven't even talked about that yet. That'll be as we learn as we progress forward. So net force is the 40 to the right divided by our mass of 20. And that's going to give us 2 meters per second squared. And we have to include our direction because acceleration is a vector. Okay? So acceleration and direction. Direction is going to be important on these problems. All right, skip a couple. We're going to look at this. All right, in this scenario, there are a couple of different things we can look at. Both objects are being pulled to the right by rope A. Rope B is pulling the 5 kilogram object. So if we wanted to find the tension force on rope B, all we care about is what's happening back behind the 10 kilogram object. B isn't pulling the 10 kilogram object, it's only pulling the 5. So to find the tension force on that, it's force equals mass times acceleration. 5 times 6. That's going to give us 30 newtons to the right. If we wanted to look at the force on B, it would be mass times acceleration, which would be 15 times 6, because rope A is pulling both of the objects. It's being resisted by both objects.
Good morning, ladies and gentlemen. Will you please rise to face the American?
Okay, so obviously we're at school and things go on. Okay, our next problem we're going to work is if you put a bag of groceries on a table, what force does the bag of groceries exert on the table? I'll draw a picture down here. What happens is you got the bag of groceries, it's sitting on a table. Okay, so it's not moving, so no force is being applied, right? Wrong. The bag of groceries is being pulled down through the table by gravity. So the force of gravity is equal to the mass of the object times g. It's going to be a positive number because we've got our arrow showing it's going down, and we don't put a negative and all that stuff all together. So 25 kilograms times 9.8, and that will give us, I think it's 249. Let me check it real quick. It gives us 245 newtons. Now, so anytime you put something on top of something else, gravity is going to pull the object through the second object. Now, if the second object can support the bag of groceries, it has to apply a force, part B, that is exactly equal to the force of gravity on the bag of groceries. So the force exerted on the table by the bag of groceries is 245 newtons. The force that the table exerts back is 245 newtons. This is an example of Newton's third law. Third law says that for every action there has to be an equal and opposite reaction. So whenever there's no movement, but anytime like you're standing, you're sitting, you're leaning against a wall, then the forces have to be balanced out. Whatever you're doing against that second object is doing back to you. All right, what is the net force exerted on a 90 kilogram race car driver while the race car is accelerating 9.4 meters per second squared? So what happens here is net force is going to equal mass times acceleration. We're finally just getting the straightforward saw from force equation. So in this one, the race car driver is 90, and he's accelerating at 9.4. It doesn't matter that he's inside the car. The car and the driver are both being accelerated at 9.4. We're only asked about the driver, so it's just his mass times his acceleration. You'll get your answer, and it'll be in newtons. So you can do the math on that. All right, let's talk about weight again. Weight, so the weight of a woman in Houston, where G is 9.8, what we're going to do is her weight, force of gravity, is mass times G, the acceleration due to gravity, which they give at 9.8. So it's just 50 times 9.8. Okay, we get her weight. Excellent. Great. Put it over here in newtons. What happens if we put her on the moon? What's her weight? Now, it's important to understand that mass never changes. Mass doesn't change whenever you're suddenly transported somewhere. Okay? Your weight changes based on the G. So your weight will change because our G is now less than 9.8. So instead of weighing 50 times 9.8, which is 490 newtons, instead of having 490 newtons of weight, her mass remains 50, but now we only multiply it by 1.7. And when you put that in your calculator, then you get 85. Okay? So the person goes from weighing 490 newtons to 85 newtons. And that's all based on the gravity. That's why when you watch pictures of people on the moon, they bounce around versus just taking steps. Because every time they take a step, if they tried to take a step in the natural manner, they would lift up off of the surface of the moon. So they have to learn to kind of leap around versus taking steps. Okay, good luck with this. Have fun. It's easy math. You just have to do it step by step.